So one thing I wanted to do was just to step back a little bit and look at how this project was structured, how the files and the directories were structured. There are not a lot of files here, but it's still useful to just sort of step back and go through how it's set up. So we certainly have our main.go file, which is the main entry point into the project. We have these two other files called gopackage.toml and gopackage.log. So both of these files are auto-generated. They're actually managed by a Go tool called dep for dependencies, and dep basically vendors your project. So it actually scans whatever external libraries that you're using, and it actually copies them into your vendor directory. So you could have a local copy of all your dependencies that's localized with your project. And B, it actually keeps these Go package and lock and toml files up to date with the exact versions. So it's a pretty common convention to actually use dep with Go projects and check in your vendor directory, assuming it's not massive. Check in your vendor directory and your lock.toml files. So tomorrow you can build your project, or someone else can build your project with the exact versions of the dependencies. So pretty straightforward vendoring. We've got another folder, pretty generic folder called utils, and currently the only file we have in there is called redis.go, which manages our Redis connection. And we have another directory called controllers, which has two files, PageViews.go. PageViews handles the post requests that are being made, specifically the setPageView method in it, and the reports.go file basically handles all the GET requests that the user is going to make against this API. So the other thing worth mentioning is that it's pretty conventional to have the name of these directories coincide with the packages. So Go manages everything in packages. So you'll see that all the files in the controllers are inside the controllers package. Page views is in controller, reports is in controller. And then we have utils, which again only has a one file, but it's inside a utils package. And just for organization and following convention, the main.go file is in the main package. So 3 packages in total. So that's just a quick overview on how the files are structured. So one thing I noticed is a little bit of confusion around naming conventions. So there are 3 things here that we're talking about. There is our actual API paths that somebody could call // or /pageviews /uniques. We have the name of the actual functions in the controller that get called as a result of people hitting those paths. And then we have the actual file names that I've actually called, so page views and reports. And after looking at this, there was actually a little bit of confusion around here. Primarily that we have a path called page views here, which actually calls a function called GetPageView inside our reports file, which is GetPageView specifically right here. But the tricky thing is, so that actually calls into the reports file, but the path /pageviews actually coincides with a totally different file, which is pageviews. So that's actually kind of confusing. It's the pageviews file, or the method setPageView inside the pageview file. It's only used by this / path right here. It's not being used by either of these, but because the path pageviews is the same as this file, it's actually confusing. We sort of have it gives the reader the impression that we're actually using the pageview files for this pageview path, but it's not. So and there are a couple of other like plural things too that we're actually going to fix right now. So first of all, I'm going to change the name of this file. Instead of page views, I want to actually call that pvlogger, because that's exactly what this does. This is the page view logger. It actually handles all the grabbing the post data and actually logging the page view. So that's what it should be called. And the set page view, that can stay. I think that's fine. And then, so the other thing I wanted to do. So now it's a little bit uh, more legible. So the slash goes to controllers.setPageView, which is inside the PV logger, and then we have two other paths right here that actually go to the reports. So let's actually make this a little bit more explicit. Instead of just slash, let's actually call this set page view. So I like that a little bit better, where now instead of just slash, from an API point of view, it's a little bit more clear. So we have three calls: set page view, which actually sets it as a pull request, page views, and uniques. So and the last thing I wanted to do was make this consistent. So we have slash page views. It should actually go to a function called GetPageViews, and uniques should be called GetUniques. So now this looks a little bit better. So set page view goes to set page view, page views goes to get page views, uniques goes to get uniques. So that was just a little. I think that the main point of contention was just this page view that was conflicting with a file that it has nothing to do with. So now that we've changed that to pvlogger, it's actually a little bit more legible. Maybe we'll go just one step further and actually make these also have gets in front of them. So now the API paths are even more clear, where you can hit either slash set page view, slash get page views, or slash get uniques, and all of them actually coincide with the appropriate method in a controller. So we got set page view, get page views, and get uniques. So that's just a little bit of just a naming cleanup I wanted to do, because it was actually confusing me too after I went back. Naming things is the hardest problem. At least we fixed it up a little bit to make it more legible. So now let's also update those methods in the files. So we'll go to our ports and change get page view to get page views, and get uniques, that's up here, to get uniques. Save that, make our compiler happy again. The other thing you may notice is that these methods are actually capitalized. So this is a convention that Go uses. Anything that's capitalized actually gets exported out of that package. So because we are calling these methods outside of the controllers package, we're calling it inside the main package. If they are capitalized, they're automatically exported. If they are not capitalized, they will not be exported. So that's just something small worth mentioning. So now, after all those changes, let's see if our code compiles. And yep, everything runs and our server is running. So good, glad we made those few changes just to make the naming a little less confusing. All right, so let's fire everything up. Make sure our project is running. I want to make sure that Redis is up. Yep, so Redis is up and running, and then we will bring up Redis commander that yesterday did not want to run. So Redis commander is running at port 8081. So if we do localhost 8081, sure enough, there is the Redis commander. You'll actually see a bunch of data that, let me make this a little bit bigger. A bunch of data that exists there from before. Different keys that were getting created. So we'll actually so now let's also make sure our project is running. So yep, so our server is running at port 8080, and we can actually test that and say localhost instead of page views, it's actually now GetPageViews. And run that. Sure enough, we actually get a JSON response back. So everything is up and running. We have our web server running. We have Redis up and running. We have our handy postman here that we'll actually use to make post requests. So good, everything is up and running. Let's actually start making some post requests. Let's make sure they actually show up correctly in Redis. And then after we log a bunch of hits by various clients, various paths and references and various GoIDs, and then we can run a bunch of GET requests to actually get those reports to make sure that we're getting all the data back. All right, so let's actually clear out all the data that exists in Redis right now just to have a clean slate. So I believe it's flush all command that actually clears all the Redis data out. So if we do a refresh here, yep, literally there is nothing that exists in Redis. Everything is cleaned out. So let's actually do a sample post request. So we are going to be posting a request to set page views. For our parameters, we'll actually create a fake client ID. So here's our client ID. We will have this GoWid, and to start out with, we will our path will have the path of index, and our reference, or sorry, the referrer is google.com. So actually, let's send this request. We should only have our server running, and we get a 200 back. So now let's look at Redis commander. Let's make it a little bit bigger and see what we have. So certainly we have a bunch of keys that were added as we successfully logged all the data into Redis as a result of the post request. So let's actually, and the piece of code that actually handles that is the PV logger code. So first, let's actually go through quickly the PV logger code just to see what it's doing, and then we'll actually go back into the Redis commander to make sure that it's actually correctly logging everything. So looking at set page view, again, from main, we actually have set page view. It actually goes to the set page view function in the controllers. So we come over here, set page view, because it is an HTTP handler. It actually expects an HTTP writer and a request object So that's what we actually pass into here, or it implicitly gets passed into here. We just as another safety net, we make sure that the request was actually a post request. The request object actually has a parse form method built in, which will actually grab all the post values and actually set them up so those values could be obtained, whether they're get or post. They're post in this case. So what we were posting back here were client ID, go with path, and or refer. So those are the values that we are getting over here. The next thing we do is we grab the current time. We create a Unix timestamp from that current time. The way I designed this API is the API expects pretty much everything is a Unix timestamp that we're passing. You'll notice even here for the actually not quite yet, but we'll notice when we actually make get requests, all the start time and end times are in Unix timestamp. I just happen to do it in Unix timestamp. It's not actually very user friendly because even during my testing, I need to take a regular time, convert into Unix timestamp to actually make REST calls. Ideally, for the user-facing stuff, it would be good to give them an option to just have a more conventional format for date. But for the time being, it's everything is Unix timestamp. For our event type, like I mentioned, we're setting our event type to be page view, and this page view, as you'll notice, actually gets appended to the key for every log right here. So that becomes part of the key. That's a static string. But certainly, this could be anything. This could be a page click. This could be some action that the user takes. This could be an email view. Whatever we want to track. That's you can extend the system to actually track other types of event other than page views. Next thing we set up something called the page view index key, and so this key or this page view index value, it's basically our auto increment value. It's just a counter, and for every request we increment it by 1. And that is basically the primary index that we are using for everything as we move further down. So this is just a counter. It's called a page view index. You'll actually see it right here in Redis. Currently it's at 1. If we were to make another request, let's actually send another request. And we do a refresh. Page view index is 2. So it's literally just a counter that we're incrementing, and we're actually going to be using that value in other Redis structures like sorted sets that we're going to be using. But that's where we actually set it up. The way we calculate or the way we create the key for that, it's the client ID that gets passed in, followed by a key separator. You'll actually see this KS everywhere. It's just a way to have a constant. Actually, now that I think about it, it probably would be better to actually define it as a constant. And it's defined in our util directory. If you go into util Redis, we have another thing we should probably do is we should probably get this Redis. I guess it could stay here because it is a Redis separator, not a general separator. I was thinking of actually moving this out of here into a separate util file, but I guess it belongs in Redis. So as a key separator, you'll notice that this is also capitalized because that value is exported. So it's exported out of this package and it's available to other packages. And right now we just have colon. We're using colon as a separator. So you'll see that over here. These are all the colons. They're the separators. So there is that. And so going back to our logger, so it's our client ID followed by colon, followed by just a static string called page view index because we're going to have a page view index. So that's where we're namespacing our auto incremented value that we're going to be using for every client. And then, of course, we do run an increment operation on it. where we actually increment the value by 1, and we assign it to page view index. This is a pretty general convention in Go, where functions in Go can return multiple values, and a lot of times what they'll do is they'll return the actual value you're expecting back plus an error. And so typically if everything goes well, error is set to nil, the equivalent of null, obviously. But if it's not nil, that means there was some error that got returned. So you'll see this convention everywhere, where if you say if error is not nil, meaning error is set to some error message, then we're going to actually print it out. Otherwise, we just move along. So after making the post request, the first thing we've done so far from this code is just created this auto incremented page view index. The next thing that we do is we actually start setting up either certainly create on the first request, but add to in subsequent requests all the remaining Redis structures right here. So here we're actually setting up their keys, and then here we are actually making all the actual Redis calls to actually set up those structures. So here we are setting up all the keys. So this is going to be, I guess it's better to go through what we're going to be creating. So for every post call that happens, we actually create a hash map, and that hash map has the convention here is you're doing a hash map set, the page view hash key, and the basically any value that you want to add to the hash map. So we're adding the GoEd path and the refer. So you'll actually see that right here. We've made 2 calls, and we've had 2 hash maps here. I'll make it a little bit bigger. So page views. So again, the page view hash key, it's the client ID followed by a separator, followed by the event type separator, and then we have the page view index, which is the auto incremented value. We're using the sprintf command in Go, just because Go is a statically typed language, and we're trying to convert this into a string. The auto incremented value that comes back as an integer. So we're just using this function right here. So you'll notice the value that's set in Redis are right here. So the client ID, page view, and then the auto incremented value. So each one of these actually gets created as a hash value. So we're going to be creating a hash. We are also going to be creating a sorted set. So basically, as I mentioned, every value or every dimension inside the hash that we want to be able to query on, I'm actually building a separate index using sorted sets. So in this case, it is our path and our refer. So both for the path right here and for the refer, we're actually creating a sorted set, and the sorted set has the Unix timestamp as the score of the sorted set, and the actual auto incremented page view index that we're using as the value. So that's what these two create. And then we have we have another sorted set which tracks, because time is time is really the main dimension of our hash map that we want to track. So we want to be able to query on just the time, which we will use our sorted set, the time sorted set to use. We'll use our page view and the path and the refer as the sorted sets to be able to query on both of those. So again, the path, page view by path key, pretty straightforward. Client ID separator, the path keyword separator, followed by whatever the path that the user has passed in that came in as a post request. Same thing with the refer. We have the refer right here, Then we have so actually let's take a look at those right here. So page view, that's the hash that gets created. There's the path, and here is the refer. So far we've had google.com as the path and index.html as the refer. And then of course we're tracking uniques as well. The way we're tracking uniques is using hyperloglog. So what this does is it sets up the key, again client ID, the separator, the word uniques, separator, followed by the date. So this is the Go formatting for date, which is basically a 4-digit year, 2 for month and 2 for day. And then so we can actually see that over here in uniques. So the way uniques are set up so far, we've had a couple of hits, and it's for today, for the 8th. So there's one hyperloglog entry in uniques for the 8th, which is today. Certainly, if we make more, it'll be logged to the same. If I change the date and I start logging for tomorrow, obviously it'll actually create another hyperloglog key in there and start adding to that. And then lastly, we have the time index key. So this actually it's better to move that along with all the other keys. I think that's better, because now we have our hash here, the three indexes that we're using for the hash, the index for the path, index for the refer, index for the time, and then we're handling our uniques. We're executing everything inside a transaction for obvious reasons. We want all of these things are atomic, so that's the right thing to do here. And then it basically runs through all the different Redis operations. So create a hash map. Here's the key that we have here, and add GoWid path and refer. Then for the three indexes, we have the time index, where so we have the time index, the path index, and the ref index. All of those are sorted sets, and the score is the Unix timestamp, and the value is of course the same auto incrementing field. And of course, the reason that works is it's an index into our hash, and the value of the hash is the auto incrementing field. So it's a good way to actually index all three based on that auto incrementing value. Hopefully that makes sense. And then lastly, we have a hyperloglog add for unique keys, and then we basically do a exec on that transaction, and everything works. Redis will actually return, I believe, the number of the number of records that got affected when you do this exec. So if we had a value here, it will return that back. But Go has a convention where if a function is returning multiple values, you can actually just add an underscore to suppress the value, because we don't really care. We just really care if only care if there was an error. So we just check to see if there was an error. If there is, we'll log it. Otherwise, we go on our merry way. So that was basically an overview of how the post works and all the different Redis structures that get created as a result of a post. And as we saw over here, everything is set up correctly. We have our key set up. We have our the hashes set up for page view 1 and 2. We have our page view index got set up, which is the auto increment value. We have our index for a path, which is path : or client ID :path : the actual path. We have a refer with the same format. We have our time index, which is the same format, and then we have our uniques. So now let's make a few more post calls just to make sure that we have enough data, and then we will go through making some get calls to make sure that reporting is working correctly. All right, so let's actually make a few more hits here, just with this client ID, this go with this path and refer. So we'll send 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we send 12 more post requests. So if we actually refresh Redis Commander, so we have, if we go to our page view index, actually, so total we've made up to 13 post requests so far. So let's actually quickly run our make a get request just to see the total number of hits that we've gotten so far. So 80, 80, and we'll do get page views, and what we need is just the start date and the end date. So we'll do, actually here it is, let's just make sure that's the correct start date and end date. So I've gotten what the start of today and the end of today is in Unix timestamp, and it's here, and end is equal to so there we go. So we made a get call that says to get page views, start time is the beginning of today, the end time is the end of today, and certainly these times could be arbitrary. And here we actually get our JSON response back. So we've had 13 total views so far. There's a start time and an end time. For the paths that we get back, since we're not passing in any path or refer parameters, we're just setting those to all. It's useful to actually get that back, just so the consumer of the API knows that, okay, we're looking at all paths and all refers. So that's that. And if we make a few more post requests, made a bunch more post requests here. I don't know how many. And if we make another call to it, there we go. So we made 38 post requests. We'll make 2 more just to make it an even 40. So there we go. We've got 40 40 hits to our sites so far. And of course, we go into Redis Commander and refresh. Everything is being written correctly. So for the page index, it's at 40, which is our universal incremented value that we use everywhere. For page views, again, we have all the hashes that we are actually logging every single request with what the path was, what the refer was. Of course, this is where you can add other dimensions to it, like the user's browser, operating system, type of device, mobile or not, all those things. So let's actually go through this code path. Let's go through the code path that gets us gets us all the page hits without actually caring about what path it is or what refer it is. So we call GetPageViews through here. GetPageViews gets called the GetPageViews in our reports file. So let's go into reports and let's go through this file to sort of trace back that or trace through that call to see where it gets called and how it works. So starting at the very top, it's worth mentioning that we have a page views type that we have declared as a struct. Go struct are very similar to C structs. essentially an object where you have the value and the type of data it's going to be storing. So it's an easy way for us to return a clean object back to the user that we marshal into JSON. So we have views, that's in64, start time, end time, path, and a refer. Certainly we can add a lot more dimensions to it if that's what we're going to be returning. And you'll notice that these all map back to what the user sees. So again, we have views, start time, end time, path, and refer. We have our type, another uniques type struct that we set up that we'll look at after. We have a client ID that we hard coded. Of course, this is a multi-tenant environment that we're running, and a particular client should only have access to their own data, so that's not something that should be passed in. So this would either be fetched from their database after the client is authenticated, or it would be in the client session or something, but that we have this hard coded for now. PV is we're declaring a pointer to a page views object that we're going to be using later on. And R is a new renderer object. We're going to use that renderer object or the renderer package really, to grab some data, specifically a struct, and actually marshal it into JSON and send it back to the browser. It can also render as just plain text, as XML. So we're using JSON. Again, we go to get page views. So let's go down to get page views. Get page views is another HTTP handler, so it expects there to be a HTTP writer and a request object available, which is being passed in. We again check to make sure that it was a GET request. So we check just the request method. And what we're doing here is we're creating a new variable called getParams, and we are instantiating a new page views struct. So views right now are 0, start time, end time, path, and the refer we actually get from our as query parameters. So we're actually setting those here. And then down here we are basically looking to see what is the user looking for. Is the user looking for just all page views regardless of the path and the refer? If that's the case, we immediately go down to here. So if the user has just passed in a start date and end date, they're looking for neither the path nor the refer, we actually come down here, which is the case we're interested in. If it's one or the other, then we go here. If they're looking to segment by path and refer, we run this. If they're looking for just a refer here, and if they're looking just by path, we run this. So we just segmented those into a bunch of utility methods that we'll look into. But the path right now we're interested in is get all page view. So that's what gets called. So get all page views, it actually gets we pass in a pointer to this getParams object that we created. So it's a page views object that we just instantiated up here, and after it gets created, we actually pass a pointer to it to get all page views, because that's what we're interested in. So get all page views, here's get all page views. It again accepts a pointer to a page view object, and it actually returns the same object back. So in this case, where we care neither about the path nor the refer, we are just doing a simple z count on that sorted set. So we have our time index sorted set, which is right here. And since this is our time index, it cares neither about the path nor the refer. It's actually keeping a track of every single hit that was ever made. And certainly we want to do it between start time and end time. So it basically does a z count on, here's our key, a client ID separator, time index, and then give me a count of everything between start time and end time. We get that count back as hits, Again, the same pattern of checking for errors to see we don't have an error. And then on that the page view struct object that was passed in, we set its views to be the hits that we got. We cast it to int64 because that's what it expects. And we want to be able to handle large numbers. For pv.path and pv.ref, we set both of those fields to all, as you'll see over here. It's just a sort of a nice way to let the client know when they get the JSON response back that for path, since they didn't pass in a path and a reference, we're actually giving them all the paths and all the references. And then we basically return that object back. And after we return it back, we actually use our renderer and our writer object to actually write that PV back marshaled as JSON, and that gets returned, and that is what you see over here. Now let's make a few more post requests for actually a different path. So we'll keep the refer to Google for path. Instead of index, we'll call this checkout. So let's make a bunch of requests to the checkout page. We're just making a bunch of requests. I have no idea how many. So we made a bunch of requests. Great. So now let's go into Redis Commander, do a refresh. All right, so here we go. So we've got 40 requests that coming from index and 34 from checkout, 74 altogether. So now let's actually look at requests just by path. So again, we have 34 in checkout and 40 in index, so let's take a look. So here is our time frame, and our path should be just index.html. Let's actually not in the index. So there we go, 40. For index, we have 40. For checkout, we have 34. And let's see if we can make a few more for checkout. Say 35, 36, 37, 38, 39, 40, 1, 2, 4, 5, 6, 7, 8, 9, 10. So 50 total requests for checkout. Let's see if that reflects it. So there we go. So now this API endpoint actually looks at if you only are curious about hits to a particular path. So checkout.html. So coming back to the code, that path is this over here, which is get page views by path. And if we were to actually go down, it's a very similar structure, where again it accepts more or less the same as all these utility methods pretty much have the same structure, except the ones that only get either all page views or only by the path of the refer are just doing a z count, and the one that gets it by both the path and the refer is doing an intersection of the two sorted sets. So coming back to just by path, again we grab a page view or get passed in a pointer to a page view object, and we do a count on the client ID separator plus path plus separator plus the actual page path, start time and end time. So that's this is the key, and then our bounds are the start time and end time. Those are the start time and end time on the sorted set for this. So again, going back here, we have our client ID. We have, followed by separator, we have path, followed by the actual path. So that's the checkout sorted set, and this is the index sorted set. And we, again, do a count on that sorted set, check for error, make sure that there is, we just actually cast it to int64, set those fields for views. Our path value, it's already set up here because the path was actually passed in. But for ref, we're actually going to pass in all because that's what we want to tell the customer. So again, you'll see it over here. When we actually pass that value in, views are set to 50. We have our start time, end time. The path that you requested is this, and the referrer, it's actually all referrers. It's everybody. So that is by path. Let's look at it by refer. So far, let's see if we have any other referrers. We don't. The only referrer we've been making post requests with has been Google. So let's actually change that. Let's actually change our referrer to be, I don't know, Instagram. So Instagram, and it's also going to do, it's also going to be checkout, let's say. So we make a bunch of requests to a bunch of post calls where the referrer is Instagram. And now if we come here to Redis Commander, refresh, and certainly another key that gets added now is the Instagram key. And apparently we have 32 hits through Instagram. So now let's take a look. So instead of our path being checkout, let's forget about the path and actually let's pass in a referrer. That's actually Instagram.com. And there we go. We have, as expected, 32 here, and we have 32 views. Start time, end time. This time, path is all because we don't care about the path. We want to look at all the paths, and the referrer is actually Instagram.com. So again, going back to the path that get query takes is over here. It's by refer. Again, pretty straightforward. Same exact mechanism as the other two, except we're doing a z count on the refer sorted set within the time bounds of start time and end time that get passed in. All right, so now let's actually make a call where we're getting we want to get hits by both the path and the refer. So our refer is Instagram.com, and let's say our path is, let's say, index.html. Hit that, and look, so we have 0, where 0 people who are landing on the index page coming from Instagram. How about checkout? Okay, so 32 people from checkout. Let's see, from Google, 50 from Google to the checkout page, and 40 from Google on the index page. So let's see, this is actually working correctly. So let's say it's Instagram again to the index page. So it's 0. So let's see, we make a few more calls today from the index page to Instagram, and let's see if we can change that. A bunch of hits, bunch of hits, bunch of hits, and now if we do a refresh, well, certainly now we have 20 where the path is index and the referrer was Instagram. So this is the more complicated, slightly more complicated example than the other two when you have both, because now what we need to do is grab the sorted set for the referrer and the sorted set for the path, and actually do an intersection. So here's that path that we take. So it's get page views by referrer and path. and we go down here. Again, the overall structure of the function is more or less the same. It accepts a pointer to a page view object, and the difference is what we're doing right here is an intersection. So let me actually make this a little bit bigger. The intersection of two sorted sets, the refer and the path. So here's the syntax for it. It's z intersection store. What this out is, this doesn't actually mean output. This is where it's actually going to store the result of this operation. So right now we just have out. This should probably be a much better name. Something like sorted. Result of path and refer, or some more descriptive name, but I'm going to leave this as is. A second argument, it actually asks for how many, Redis wants to know how many sorted sets you're going to be doing an intersection on, so we have 2. The next 2 are the actual keys of the 2 sorted sets, so we have the path sorted set and the refer sorted set. And then the parameter we want to pass it in is weights, is what are the bounds, the lower and the upper bounds that we want to look for. Of course, is start time and end time. So that's what we run. And again, check for errors, set the views to be the hits, and actually return that struct. And that struct gets marshaled to JSON and returned. So this is all obviously working correctly. So we'll actually take a look at, if we do a refresh on Redis command, or you'll actually see now here's that out set that the result actually get intersected and stored to. And I'm not doing this at the moment, but this is something that should be cleared out. Because everything is getting stored in memory. If this is just some sort of a little bit of scratch space that we are storing the result of an intersection with, we should clear this out, because it's after we get the count, it's superfluous data. So that's something we can do to make this a little bit more efficient. So last thing we'll look at is how we're handling uniques. So if we go into our reports directory and look at the GetUniques method right here, unique has it's an interesting query. And we can certainly design the get query any way we want, but all uniques does is it only accepts a single parameter called t for time. And you give it a Unix timestamp of particularly any time, and what it'll do is it'll actually give you the daily, monthly, yearly for that day. So for example, if I give it today's date, it will tell me what the daily count is for today, for whatever the current month is, and for the current year. So it's pretty flexible. You can literally give it any day and you'll get all 3 dimensions. We can certainly get more fancy and add hourly to it too. That way, whatever Unix timestamp that you give it, it'll calculate what that particular hour is and give it to you for that hour, for that day, month, and for the year. So to see it in action, basically here is our call, get unique time. It's the time right now in Unix timestamp. If we hit enter, certainly we've got the time that gets returned is it's today. And for daily unique, we've only had 1, monthly 1, yearly 1, obviously. So we've only been making requests with 1 GUID, which has been this GUID. So we can actually change this up and give it a different GUID and send a bunch of these posts. Let's send a bunch, again with the path being index and refer being Instagram. We send a bunch of those, and when we do a refresh, certainly we have now 2 uniques for today, and certainly for this month, and certainly for this year. So that's essentially how this works. In order for us to be able to have different numbers for monthly and yearly, we certainly need to log more requests for different months and years, which I'm actually going to do right now, just so we can go back and test the other two features on this. So I've gone ahead and added a bunch of fake data for different years and months. So if we go into Redis Commander here, I do a refresh and take a look under our uniques. Now we have a couple of years, 2017, 2018, and under 2017 we have November and December. Under November I have November 15th, under December 15th, and actually the same thing for almost the same thing for these guys. For 2018 we have May 15th, there's some entries there, and June 8th that has some entries. So if we go and we query, one thing to note is I actually just cleaned up the code a little bit. So you no longer, the client who is using the GetUniques get query doesn't need to pass in a Unix timestamp. It was a little cumbersome even for me, because in order for me to test it I need to convert it all to Unix timestamp for various dates. So now you can just pass in a regular year, month, day format here, and you'll actually get the right result. So actually let's take a look. So let's start with 2017 11. And 15. So we have, for that day, we have 3 daily uniques for that day, certainly 3 for that month, and 4 for that whole year of 2017. So it's nice that we actually get all this information in one fell swoop. Let's say if there are any for, so these two, for any other days, these two values should stay the same. Monthly should be 3, and yearly should be 4. But the daily should change because we're actually changing the date here. So let's say for 16th, nothing. For 17th, certainly nothing. So that is working well. Let's see if we have any other day in November. No, that was the only day. And then for December, we should have some. So let's say if we do for December 17th, it's the same, but what we want is December, that's also 15th. For 15th, yep, sure enough, we've got 3 daily uniques, 3 monthly, and then 4 yearly uniques. And now for 2018, we have just basically May 15th and June 8th. So May 15th. Yep, so we've got 2 uniques for the 15th and 2 for the month of May and 4 for all of 2018. Let's see if we do the 16th. Nope, for the 16th. And let's do June 8th. We got 4 for today, 4 for the month, and 4 for the year. So, so that works pretty well. Now let's actually look at how the code works for this. The code for the uniques is certainly a little bit more complicated than the code for just getting the views. So let's go into the reports. Earlier we already looked at the page view struct. So we're going to be looking at the unique struct. We have a similar thing right here where you'll see that this struct coincides with the struct that the user gets returned marshal as JSON. So we have dailies, monthly, yearly, and certainly the time I should probably change this to date, but that's okay. The time that the user requested. So if we go to uniques, here is our GetUniques method. Let me actually make this window a little bit smaller. Actually, we'll leave it be. We'll leave it bigger. So let's actually run through this. How does it work? Like I said, I actually cleaned this up a little bit. So now, instead of parsing a Unix timestamp, we're just getting the actual date with slashes. So again, we make sure that it is a get param. We get the d get param out of our URL. When what we're doing is we're basically, because later on we'll need to match keys, so what we're doing is we just want to get the components from the year, month, and day. So we're just taking that string that the user just passed, the string right here, and splitting it at the slash. If there was any issue with the user not formatting their date correctly, or they were using a different delimiter, we actually throw an error. So let's say if I was trying to, I'm like, oh, maybe it's separated by dots. Instead, we get an error that says, no, please format your date this way. Now, again, what I like is that in one action, we're actually giving the user daily, monthly, and the yearly uniques. So let's actually look at the daily first. So daily is pretty straightforward. We are doing a pf count, which is basically just a count of uniques on a hyperloglog object. So the key that we're looking at is the client ID separator uniques. Actually, let's go to commander. Uniques followed by our date component, all the date components. So year, colon, month, colon, day. So that's what we want to. This is the key that we want to do a count on. So if we were to look at Redis commander again, this would be a very specific day right here, right? So we want to do the client ID, uniques, the year, month, oh sorry, this right here, right? So the exact day, which is the 15th. And that just does a pf count. So that one is pretty straightforward. It's the other two that are more tricky. So we have our monthly uniques that we're calculating and yearly uniques that we're calculating. So in general, the goal here is, what we want to do is, whether it's monthly or yearly, we actually match all the keys in our system that are for that month or that year. So for the month, we're actually going to be aggregating up to 31 keys, one for every day, and for a year, at most, we're going to be aggregating 365 keys to actually get the unique across the year. So let's actually follow that path. So we have a helper method called query uniques that actually helps us. What we pass to it is the pattern that we want to search for. So if we're searching for monthly uniques, we want to be able to search for anything that's the year, colon, month, colon, star, right? So basically wildcard after that. And then for yearly uniques, we want to look for all the keys that are just the year, followed by colon, followed by star, and we'll look at that after. So let's actually call query uniques for monthlies. So here is query uniques, and again, it expects the key pattern to be passed in and the result key. The result key is going to be the pretty much the same format where we have. Let's see, where do we use the result key? Can give an example. So yeah, it's right here, right? So it's just the client ID followed by the result key, and over here it is yearly uniques, and monthly uniques. So the first thing we do, and I was actually getting some weird issues before, is if these exist already, we actually delete them. So in this case, because what was happening was, with the way Redis behaves is that if the result key is set, meaning you've done a previous calculation or a previous count on monthly uniques, and that key is set, if you do the next query and the count is 0, it will actually leave that key alone. It won't reset it. So you're getting old results back. So we actually want to explicitly clear any result keys out, whether it's the monthly unique or the yearly unique, before we actually read the result. So the first thing we do is we are using another helper method called GetMatchingKeys, and again, here's the pattern that we were talking about, where the client ID, it's uniques followed by the key pattern, and the key pattern is either year colon month or just the year, and then followed by the star. So either we aggregate all the keys for the whole month if it's just a monthly unique, or for the whole year. So let's actually follow that out. So GetMatchingKeys, again, it gets the pattern. Here is the matching key method. It gets the pattern that we want to look for. Now, this is probably the most tricky method, mostly because of the type safety or the type strictness in Go, plus how this Ready Go client works within Go. And we have to do a little bit of gymnastics here to actually get it to get us the matching keys. So we will, and then we'll also see a little bit of wackiness back here, but we'll actually go through that. So anyway, so get matching keys. We do a scan, and the way the scan works is the way the Redis scan function works is that it's a scan command followed by an iterator. So it almost behaves like it's a pager. So you send it an iterator on where to start, and it'll actually send you back the results. And then the next result, it'll actually start at the next, wherever the next iterator falls, followed by the command match. Then we give it the pattern, and it expects a count, the maximum number that you expect. So for us, at any given time, it's going to be no more than 365, because our highest resolution is, resolution is a year. So 365 is the maximum. So we do a scan, and we actually get an array back. And the way it works is that the first element of the array is the iterator, and the second element of the array is the matching key. So that's what we do. We basically grab, there's some Redis helper functions called redisInt and redisStrings that give us the right data type, but we grab the first value as the iterator, and the second value as the actual key that matched, and we append. We have keys right here. We have a string of, or an array of strings set up over here, and we basically append those keys, the matching key, to the keys array. Now, again, after it completes, the iterator actually gets set to 0. So if any times iterator is 0, we actually break out. So overall, the structure is pretty straightforward. Just a little nuances on how Redis and ReadyGo, the Go Redis library, work to be able to execute this command. So that's just a little tricky, but otherwise not too bad. So again, a for loop behaving like a while loop, waiting for the iterator to set to 0 when we break. We do a scan on keys, we get the key back, and grab the key and keep appending it to the keys that we have going. So after we have a list of all the keys, we actually returned the keys. This is just a formatting statement that I have in here just to make sure that we're getting the right results back. So we returned the keys. When we return the keys, we come back here. So now matching keys has all the keys that we're matching for a given pattern, whether it's all the keys for the given year or all the keys for a given month. And now because of again type strictness in Go, there's a little bit of craziness that happens here before we can actually do a count, before we can do a merge and then a count. So what's happening here is we are creating an array of strings. So the whole goal of this is that we want to be able to construct a command followed by all its arguments that we can actually send to Redis. So that is going to be, so the pmerge command, which basically merges a bunch of hyperlog log objects. The syntax it uses is the command pfmerge followed by the destination where Redis is going to store the result of that merge, followed by all the objects that we're looking to merge. So that's what we're basically constructing, like through this craziness here. So so what we're basically doing is we're creating a array of strings here, and the first, and what we're instantiating that really with is our result key. So that's where we want the result of the merge to be stored in by Redis. So that's the going to be the first argument, and then all the matching keys we're actually appending afterwards. So it's the order is going to basically be where we're going to store it, and then all the stored keys. So that ends up being in combined keys. And now the tricky thing is, since this ready go, this do method, what it expects here, as you can see, it actually expects an array of interfaces. So an interface, there are a lot of parallels to interfaces in Java and other things, but an interface, basically an empty interface specifically, can store any type of data. And because this .do method, it's a variadic method basically, where it can expect an n number of arguments. Since those arguments could be of any type, the way they handle that is by accepting an array of empty interfaces, just so you could have you can pass in an argument to Redis followed by any number of commands, and those, any number of arguments, and any of those arguments could be of any type. The only way they do that is through using empty interfaces. So because that's the expected input into our do command, what we need to do is we need to take our array that we created here and essentially convert it into a slice of empty interfaces. So that's what we're doing here. So we've appended our matching keys that we got from here onto the resulting key. Now we need to take that and convert this whole thing into a slice of empty interfaces. So that's what we're doing over here. Over here we have S, where that makes into we create an empty a slice of empty interfaces. The length of that is our combined key, because it's going to be the same length, and that is basically our the result key plus all the matching keys. And we basically do a for loop through it, where we the index of our slice here, we actually assign the value from the combined key. So basically we're iterating all the combined keys and setting setting the value of our empty interfaces to all those keys, if that makes sense. So here we had an array, and we're just converting this array. We're iterating through this array, and we're converting this array into a slice of empty interfaces, just because that's what the expected input here is. So sometimes working with Go is a bit of a pain in the ass, and this is one of those cases. So anyway, so now we arrive here. So Go also uses this syntax where if you actually have a slice and you're passing that slice into a function that expects a variable number of arguments, you can actually do this dot dot dot. Use this dot 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 syntax, and it'll actually basically the spread operator. It'll actually spread all those arguments out, however many there are. So we finally, after all these shenanigans, we have our matching keys. We combine all those keys into an array. We convert that array into a slice of empty interfaces because that's what .do expects. And now we finally send it to our pfmerge. So pfmerge again grabs a bunch of hyperlog log keys and combines them. So after we combine them successfully, now finally we can actually do a count on it. So remember, the whole point of this was to try to find uniques over a month or over a year. So that's exactly what we're finally doing here. We do the count, and then on the result key, and then actually basically return those uniques back. So now let's follow this back. Our return uniques, they get returned back here again, whether it was the monthly or the yearly gets returned. And here we are creating a new struct of type uniques that we used here. For daily, we have the daily uniques. We cast the values to int64, obviously, because that's what the type here is. And then we have our monthly and our yearly. The time is whatever the user had entered. We just echo that time back. And then again, we marshal it as JSON using a renderer and actually send that back. So I'm sure this can be streamlined a little bit more, but really the tricky thing that happens was in matching keys, just because the scan function is a little weird with that iterator. So you have to handle the iterator if you're going to actually use the scan function to get a bunch of matching keys. And then a little bit of a pain here was how to actually send to pfmerge all the arguments in a way that Go and Redis can understand. So that was a little bit of craziness here with creating an appended string and then creating a slice of empty interfaces, and then finally sending that to pfmerge and having pfmerge understand through ReadyGo what we wanted to do. But it ended up working correctly. So that was it. That was the last bit of code. If you have any questions, let me know. Great, thanks.